Module 5 Joint Probability Distribution. So this is the last module of this semester. So module 5, under that there are two topics. One is joint probability distribution, another one is sampling theory. So under this you will get one question for the semester exam. So joint probability distribution. What do you mean by joint probability distribution? Name only suggests joint, right? We are joining x as well as y. So let x and y be two discrete random variables. Then the joint probability function of x and y is given by p of x equal to x, y equal to y is equal to f of x comma y. So far we have dealing with only single random variable. Now we have to combine here two random variable, that is p of x equal to x, y equal to y is equal to f of x comma y, where f of x comma y satisfies the following condition. One is it should be positive, and the one is sum should be equal to 1. Here sum consists of both x and y because the function f consists of both the random variable x as well as y. So these are the two conditions it need to satisfy in order to form the joint probability function. Now let me go through the joint probability table. For that we need the random variable x, random variable y. So random variable x I'll take x1, x2, etc. xn, and random variable y I'll take a y1, y2, etc. yn. Then p of x equal to xi, y equal to yj is given by f of xi comma yj, which is equal to jij. So whenever it is f of xi yj, what do you mean by that? Joint j I j, ith row and jth column. So remember the joint probability distribution. We denote f of xi yj as jij, probability p of x equal to xi, y equal to yj. So that I'll denote it as jij. Now we have to form the joint probability table in the case of problems. How to do it? I'll illustrate. You see here, you need to write random variable x here, random variable y. So make a partition over here. So this column consists of random variable x values. So x values given, you need to write it over here, and y values you need to write it over here. Clear? X values here, y value here. The last column is for summing up the values. Okay, you write sum column here. Last row is also we need to sum the probability. So when you sum it, the answer should be 1. Always the last entry should be always 1. When you sum this here, it should be 1. Similarly, if you sum these terms, you will get 1. And what are the terms inside here? So these are nothing but, see, f of x1 y1 probability distribution. This consists of f of x1 y1. This is f of x1 y2. So this depends upon x1 and y2. This depends upon x1 and y2. Similarly, last one, function of x1 comma yn. So joint probability we denote it as 1 1. First row, first column, then first row, second column, first row, third column, first row, nth column. Similarly, since we have taken m random variable, here mth row first column, mth row second column, mth row third column, so on, mth row nth column. Now here, see, g of y1, g of y2, this you will get by adding this, okay. Adding the first column, you will get g of y1. Adding the second column, you will get g of y2, so on. Adding the nth column, you will get g of yn. Similarly, here row wise you need to add. When you add the row wise, you will get f of x1. Here when you add these terms, you will get f of x2. Similarly, here this when you add, you will get f of x3. And if you add jm1, jm2, you will get f of xm. So here these are called as marginal distribution of x. So f of x1, f of x2, etc. f of xm are called as marginal distribution of x. And here these are called as g of y1, g of y2. They are called as marginal distribution of y. And I told you, always the sum of marginal distribution of x is always 1. Sum of marginal distribution of y is always 1. Now let me see some formulae related to this. See, I told you, if f of xi into g of yj is equal to jij. Suppose if the product is nothing but jij, then we say x and y are independent. What is the meaning of this? See, if f of x1 and g of y1, when you take the product of these two, if that is nothing but j11, then we say the two variables are independent. X and y are independent. Similarly, so if f of x2 is same as into g of y2, if it is j22, then we say it is independent. Or if I take, see, f of x1 and g of y2 is a j12, then we say what? It is independent. So what is the condition for independent? If f of xi into g of yj is equal to jij, then the random variables are said to be independent. So in order to check the independence, just you need to multiply the two things. If it comes out as, if you multiply this and this, if it comes out as j11, then we will say what? It is independent. Now, next formula is expectation of x and y. What do you mean by expectation of x and y? Mu x. Another symbol is E of x. So, formula for expectation, you know, sigma xi into f of xi. And similarly, expectation of y, that is E of y, is given by sigma by j, g of yj. And expectation of x into y is given by sigma xi into yj, jij. Okay, so these are the expectations of x and y, mu xy, that is E of x into y. So summation xi into yj, jij. So these formula you need in the problem. Then variance. What is the formula for variance? Sigma x square is equal to expectation of x square minus expectation of x whole square. So here expectation x you will get from this. Then take the square. And here, what do you mean by expectation of x square? Expectation of x square is nothing but sigma x square f of x. See the difference? Expectation of x square is sigma x square f of x. That's it. Similarly, the formula for y and then covariance. Covariance of x comma y is nothing but expectation of product xy minus e of x into e of y. So to calculate the covariance of x comma y, the formula is expectation of x into y minus expectation of x into expectation of y. Then correlation of x and y. So correlation of x and y is given by covariance of x comma y divided by sigma x into sigma y. So that is called as correlation. Correlation of x and y. So in order to calculate correlation, you need covariance of x comma y. Also you need sigma x and sigma y. So all these things require if you want to calculate correlation. And then if x and y are independent, then expectation of xy is always equal to what? Expectation x into expectation of y. So there are two things you can check when x and y are independent. If x and y are independent, if it is the product is so, then also we can say x and y are independent. And suppose if x and y are independent, then what we can write? The expectation of xy same as expectation of x into expectation of y. This also you can check. Okay, whenever they are independent, expectation of x into y same as expectation of x into expectation of y. So when you can you see here, whenever x and y are independent, expectation of xy becomes expectation of x into expectation of y. So when you put it here, see expectation of x into expectation, is it 0? Covariance of x comma y becomes 0. So once covariance becomes 0, when you put it here, what about the correlation? Correlation also 0. So this is a very important condition. Whenever x and y are independent, whenever x and y are independent, covariance of x comma y is equal to 0 and correlation x comma y is also equal to 0. So these are the important notes under joint probability distribution. Next recording we will see the problems under this. Thank you.